Hello and welcome everyone to lecture 11. In this lecture, we will be continuing in the MOSFET transport that we started in the last lecture, lecture 10. So in this lecture, we will see how the MOSFET characteristics IDVD and IDVG curves look like. So today's lecture, we will be covering the topics that is discussed in the section 2.2.2 in the textbook by Pire. All right. So this is what we derived in the last lecture. So ID, when VG is smaller than the threshold voltage, we call this region cutoff, and then the current is 0. And when VG minus VT is larger than the drain voltage VD, then we say the linear region, and in this region the current is linearly dependent on VG minus VT, and it also depends on the drain voltage VD. And when the drain voltage is larger than Vg minus Vt, the current is proportional to the square of minus Vg minus Vt, and it does not depend on the drain voltage. And also we call this current the saturation current, and in saturation current again the drain voltage only depends on the gate voltage Vg and not the drain voltage. So let's first look at the IDVD characteristics. So what we want to do here is to plot ID as a function of VD for different values of VG. So in the y-axis we have ID, and the x-axis we have VD. Okay, so first let's consider the case when, say, VG equals 0.5 volts and our threshold voltage is, say, 1 volt. Okay, so clearly in this case Vg is smaller than threshold voltage, so our ID is 0. Alright, so in this case we will get a curve. Okay, so it should be exactly 0 here. So this curve here is for Vg equals 0. Vg equals to 0.5 volts. Now also when you have Vg equals 1 volt, so in this case also Vg is smaller than Vg is equal to Vt, and also in this case our drain voltage, our drain current will be 0. So as long as Vg is smaller than or equal to 1 volt, the current will be 0. Okay, so let's say this is our case 1 and this is our case 2. Okay, so now let's consider the case when our Vg equals 2 volts. Now for the linear region, so we need to find out what range of voltage of the drain. So the drain voltage, the transistor is in linear region and saturation region. So for linear region, our drain voltage is smaller than Vg minus Vt, and in the saturation region our drain voltage is larger than Vg minus Vt. Okay, so for Vg equals 2 volts, it's in the linear region when Vd is smaller than Vg minus Vt. So we calculate what the Vg minus Vt is. It's 1 volts. So that means that as long as drain voltage is smaller than 1 volts, it will be in the linear region. Now in the previous slide, what we have shown here is that in the linear region ID is proportional to Vg minus Vt multiplied with Vd minus half of Vd squared. So it's a quadratic equation. So let's say here this is 1 volts here, and as long as Vd is smaller than 1 volts, it will follow this equation here. So this curve will look something like this, and when Vd is larger than 1 volt, our ID will be equal to saturation current. So ID is equals to ID sat, and which is simply proportional to Vg minus Vt square, and it does not have any dependence on the drain voltage, so it will be a constant as a function of drain voltage. So this curve will afterwards look like this. It will be a straight line. So this is the curve for Vg equals 2 volts. Okay, so this was our case 2, and say for case 3 we have, say, Vg equals to 3 volts. So then it will be in the linear region for as long as Vd is smaller than Vg minus Vt, and Vg is 3 volts in, so it will be linear region as long as Vd is less than 2 volts. So this is the 2 volts here. So this curve will look something like this, and when it's larger than 2 volts, it will follow this equation where it will become independent of Vd. So then this curve will look something like this, and this is for Vg equals 3 volts. Now let's say we also considered the case when it's Vg equals to 4 volts, and in this case it will be in the linear region when Vd is smaller than 4 minus 1, which is 3 volts. So if this is 3, this curve will look something like this, and then when it's larger than 3 volts, it will be constant, and this is the case for Vg equals 4 volts. All right, so there are a couple of important points, important features that we must take note of. First thing is that there is a boundary here, and on the left of this boundary the transistor is in the linear region, and to the right of the boundary it's in the saturation region. And the second important thing is that ID is proportional to Vg minus Vt. So that means that if this much is x, okay, so this much is x and this much is y, then y divided by x is 3 minus 1 square, basically this factor Vg minus Vt, and x is for 2 minus 1 square, so this will be 4. So if this is, so the saturation current for 3 volts will be 4 times larger than the saturation current for 2 volts. And similarly, if this much is Z, then Z by X will be 4 minus 1 square by 2 minus 1 square, which is equals to 9. And because of the square law dependence of the saturation current on V square dependence of ID on Vg minus Vt. Alright, so this curve was not drawn to the scale, but remember in this particular case where the threshold voltage is 1 volt, the saturation current or the maximum current that we will get out of the devices for 4 volts will be 9 times that for Vg equals to 2 volts, and the saturation current that you will get for 3 volts will be 4 times larger than that you would get for 2 volts. So this is the one of the important features of the square law current. The saturation current is proportional to the square of Vg minus Vt. So that's that. So here we have plotted the same curve. So the same analysis is shown here. So now let's look at the IDVG characteristics. So what we want to do here is to plot ID as a function of Vg for different values of Vd. So just like the previous case, the y-axis is ID, but now the x-axis is Vg. So again, just like the previous example, our threshold voltage is 1 volts. So first let's find out the relationship for linear and saturation region. Just write down the relationships for linear and saturation region. So in the saturation region, we have, so in the saturation region, what we have shown is that the saturation of Vg minus Vt is actually smaller than drain voltage. So for a given drain voltage, the transistor will be in the linear region when our gate voltage is smaller than Vd plus Vt. Okay. And in this region, our drain current will be just proportional to Vg minus Vt square. Okay, and in the linear region, our Vg minus Vt is larger than the drain voltage, which means that as in this region, our gate voltage will be larger than Vd plus Vt. And we have another region which is the cutoff, and in this region our gate voltage is simply smaller than threshold voltage, and in this case our ID is simply 0. Okay, so for the linear region, the current is proportional to Vg minus Vt multiplied with Vd minus half of Vd square. In other words, in the linear region, our drain current is a linear function of Vg minus Vt. Right. So now let's consider the case when our drain voltage is 2 volts. So for when drain voltage is 2 volts, it will be in saturation region when Vg is smaller than Vd plus Vt, which means 3 volts. All right. Okay, so it will be in the cutoff region when gate voltage is 1 volt. So this curve looks like this. So say this is 1 volts here and this is 3 volts here. So between 1 volt and 3 volt, it will be in the saturation region. So it will be a quadratic function of Vg minus Vt. So it will be like this. And in the linear region, it will go into the linear region when Vg is larger than Vd plus Vt, which is larger than 3 volts. So above 3 volts, the current will simply be a linear function. Okay. So between 1 volt and 3 volts, it's in saturation region, and here the current is a quadratic function of Vg minus Vt, and above 3 volts of gate voltage, the drain current will be a linear function of Vg minus Vt. So let's write it down. Between 1 volt and 3 volt, it's in the saturation region, and above 3 volts, it will be in the linear region. Okay, and this curve is when Vd equals 2 volts. Okay, now let's consider the other case. Vd equals 3 volts and it will be in cutoff when it's smaller than 1 volt, and it will be in saturation when Vg is smaller than Vd plus Vt, which is in this case 4 volts. So let's say 4 volts is here. So let's use a different color now. So in this case, between 1 volt and 4 volt, it will be a quadratic curve that looks like this. So excuse my drawing, but it will be a quadratic curve here. And when Vg is larger than Vd plus Vt, which means larger than 4 volts, it will be in linear region, and here beyond this point it will be a linear function. All right. So between, for Vd equals to 3 volts, the MOSFET will be in saturation region between 1 volt and 4 volt, and in this region the current will be a quadratic function of Id, and above 4 volts it will be in linear region, which means that in this region the current will be a linear function of Vg minus Vt. Okay, so we have plotted the same curve over here. Great.